We've looked at several applications so far where we multiply by the same matrix repeatedly. Certainly with Markov chains, but also with like the steady state vectors we looked at a little earlier, and linear transformations and computer graphics. And in a few more sections, we'll analyze discrete dynamical systems, which also do that. So it's worth looking at that process a little bit more of multiplying by the same matrix over and over and over again. So suppose you've got some matrix A, and you maybe want to multiply by it 4 or 5 times. So you want something like a to the 4th, right? So let's say that A is 1, 2, 3, negative 4. And if you had to actually do a to the 4th, it would look like this. 3, 4. 2 by 2s aren't that bad, but that's not much fun to multiply out by hand. Your calculator, of course, can handle it just fine. So you can put in 1, 2, 3, negative 4 to the 4th power, and you get out a fairly big result, which again makes you happy you did not multiply this out by hand. But even on the calculator, the algorithm it's using is not terribly efficient in the sense that it's actually doing the same number of computations that you would have done right here by hand. Which is fine when you're doing it 2 by 2 to the 4th power. Your calculator can handle that. You could even do it by hand. It's not so fine when you're doing it 10,000 by 10,000 to the 500th power. Obviously, you never do that by hand, but even your computer or calculator is going to struggle with that if your algorithm's not efficient. So let's talk about getting a little more efficient with multiplying matrices. So let me start you off with just a detached example here. So let me talk about maybe 3005 to the 4th power. Obviously, this is a diagonal matrix. The only non-zero entries are on the diagonal. Well, actually, let's just start with squaring it, because I think that will illustrate the purpose well enough. Okay, so when you multiply this out, use your favorite way that you think of multiplication, but first row, first column, it says 3 times 3, which I'm just going to write as 3 squared. And then you get 0 there, 0 there, and you get 5 squared there. And I think you can probably guess it's no big stretch if you multiply by one more copy of 3005. It literally says 3 times the first column, 5 times the second column. So you would now get 3 cubed and 5 cubed. And in general, 3005. Actually, let's be even more general than that. And let's just say A and B. Got A there and a B there to the kth power. Would be A to the k 0, 0, B to the k. And this works. This is not just 2 by 2s. This does work for any size diagonal matrix. If you raise a diagonal matrix to a power, the result is just the diagonal entries raised to that power. So there's one particular example where raising a matrix to a power is easy. Again, you can basically do it by hand, and certainly more computationally efficient for your calculator or computer. So let's talk about something called diagonalization, which sounds like a made-up word. And I guess well, all words are made up, right? Somebody made up a word. Somebody made up every word. But anyway, diagonalization is the idea of making use of the power on the diagonal process that we just looked at a minute ago. So it says a matrix is diagonalizable, another made-up word. So not every matrix can be diagonalized, but if it is diagonalizable, then you can break the matrix down this way into A equals an invertible matrix B and a diagonal matrix D. So it's P times D times P inverse. And let's look at how that would be helpful. So now let's say you want A to the fourth. And rather than writing that out as A times A times A times A, I'm going to write that out as P times D times P inverse times P times D times P inverse. There's 2 copies. P times D times P inverse. 3 copies. P times D times P inverse. There's all 4 copies. And notice what happens here. Matrix multiplication is not commutative. I cannot rearrange these P's and D's and P inverses, but it is associative. I can choose which ones to do first. So I could certainly choose to do that set first, and that set, and that set. P inverse times P is the identity, and the identity times D is just D. So this simplifies to P times D, and this goes to 1 basically, and so does that, so does that. So D, 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 so P times D to the fourth times P inverse. And now we're happy, we are smiling. Because we like doing diagonal matrices to powers, that's easy. So now instead of having to multiply by 4 full matrices to do this multiplication, I can do 1 matrix, a diagonal power, which is easy, and 1 more. So really I'm just getting 2 or 3 matrix multiplications rather than 4. And more to the point, if you wanted to do A to the 100th, it would just be P D to the 100th, which is easy, and P inverse. And that's where the efficiency really comes in, is higher powers than 4. So that's the idea. Seems helpful, right? If getting this PDP inverse isn't too much work. Once we have it, it'll be useful. So let's take a look at an example. So here's a 2 by 2 matrix. And for the moment, I'm just going to tell you what the P is and what the D is. So the first thing I'd like you to check is just to see if the factorization's actually correct. So there's A, and the claim, so this is A. The claim is that it's equivalent to P times D times P inverse. So it should be that if you multiply 3, 5, 1, 2 times 2, 0, 0, 1 times the inverse of P, whatever that is, that you get the original A. So that's the first thing I'd like you to check, is just to make sure that we actually have it right here, or that I've given it to you right. So you will need to actually figure out P inverse, and then you'll need to multiply P times D times P inverse. So go ahead and put the video on pause for a second, and then come back, and we'll work through it together. Okay, so welcome back. Hopefully this worked out all right for you. First thing we should do is find the inverse of P, which you can certainly do with a calculator, but since it's a 2 by 2, you can also use the little 2 by 2 inverse formula that we have, which says change the sign on the, sorry, that's not right. a little while since I've used that formula. Change the entries, swap the entries on the main diagonal, change the sign on the off diagonal, and then we also need to multiply by 1 over the determinant, which happens to be 6 minus 5, happens to be 1 over 1, so multiplying by that doesn't change anything. So this should be our PDP inverse, and let's actually multiply it out to make sure that it becomes 7, negative 15, 2, negative 4. And I'm not going to do that by hand. I'm just going to use a calculator. So here we go, moment of truth. I've got that multiplication in the calculator. And multiplying those three out does indeed give you 7, negative 15, 2, negative 4. All right, so we have found, or I have found, I've given you a proper PDP inverse factorization. And again, if you want something like a to the 20th power, that would be 3, 5, 1, 2 times d to the 20th power, which is 2 to the 20th, 0, 0, 1 to the 20th, times 2, negative 5, negative 1, 3. Again, it's easy for a calculator to do. You could probably even do this one by hand. I'm not going to, but you probably could if you had to. Okay, so that's sort of how it works when you have a PDP inverse factoring and raising powers. In the next video, we should take a little bit of a look at how you actually find a P and a D yourself.